morning, everybody. I am Abbas Sibai, doctorate student at Sapienza University of Rome. My professor is Marco Valente. I'm here to present a study and design optimization of hollow bricks as a possible application for rubbercrete mixture. Tires are being thrown in seas, lands, and streets. As shown in the figure below, this research project said the reason behind tire recycling. Generally, in most countries, there are no strict regulations regarding tire disposal. Hence, tires end up in seas, lands, as well as being burned, harming the living beings and the living being and in the environment. The work is organized in 4 experimental stages: production of rubber cement mixtures, evaluation of properties and mechanical, thermal, elasticity, and characterization of hardened samples, simulation of molds for brick production with standard hollow bricks as square and circular, which they are the general shapes of the hollow in the brick, as well as unconventional geometrical shapes such as fractal, hexagonal, and hybrid. The hybrid is the combination between fractal and hexagon structures for the achievement of topological optimization. The third step is about multi-physics analysis, study design, and numerical analysis of rubber cement building components with functional engineering properties. In this stage, topological optimization studies will be performed to obtain brick samples. The fourth step is about the production of a brick according to the chosen sample from material and characteristics. To date, we have completed part 1, 2, and 3 of the research as related to aggregation of material, 3D design of molds, multi-physics analysis studies. Below, we report the studied formulations and some experimental results on our 3D design. Finally, our research proposal for scientific corporation is summarized. To start with, tire rubber aggregate. The two type of rubber polymer particles that is supported from ETRA were selected and used to produce the rubberized mixture. The aggregates were obtained by ambient mechanical grinding of end-of-life tires, rubber powder from 0 to 1 millimeter range size, and rubber granules from 2 to 4 millimeter range size. The average density of rubber particles was evaluated by micrometric AccuPike 1330 high pyknometer. The general materials that have been used in this aggregation are the sand, cement, water, and WC ratio. Rubber cement mortar formulations. Starting with reference formulation, several rubber and volume replacements were performed to obtain 4 rubber cement mixtures, labeled as the reference, mixture 2, mixture 3, 4, and 5. In each mix design, 2 parameters are modified: type and amount of rubber aggregate that is used, and water dosage. The samples are according to the 4 mixtures with the sand partial or total replacement and according to the aggregate proportion of sand and rubber. So we can say that the amount of rubber that is being used varies between 50, 100%, 25 to 75%, according to each sample. In the follow table, the composition of rubber cement mortars referring to 1 meter cube are listed. And we can see that in each mixture, the amount of sand that starts with mixture 2 was 550 kilogram. We can see that mixture 3, 4, 5 were been totally replaced with cement proportion around 800 kilogram. Rubber powder and rubber granules differs according to the mixture listed below. Sample preparation of experimental program. We can see here that there's a sample of cutted material that goes between 48, 42, 22 millimeter and 50 millimeter side cube. Here also there's like a 40 to 130 millimeter beam. Also, it was being used as a sample preparation. Several physical and mechanical characterization on material compounds after 28 of ambient curing included. The bulk measurement. Bulk density was obtained by dividing the mass of ovened dried samples into its geometric volume at 110 Celsius for 48 hours. We can see that the reference was 1927 kilogram per meter cube, but according to the percentage and mixtures, it varies between 1645 reaching 14868 at mixture number 5. As permeable porosity measurement, vacuum saturation method was used to evaluate the porosity degree in the investigated samples. The porosity was, for reference, 33% compared to the mixture 2 until reaching the mixture 5. It also varies between 26 reaching 25.7%. Supportivity test is the tendency of a cement-based material to absorb and transmit water and other liquid by capillarity. Supportivity index was evaluated in accordance. The test is based on determining the water absorption rate by measuring the mass increase of the sample as a function of time and in the unidirectional flow condition. As for reference, it was 4.42. We can see that for mixture 2, 3, 4, and 5, it varies from 4.14 at mixture 2, reaching 5.03 at mixture 5. All cement-based mixtures can be classified as very good since their supportivity values are less than 6.25 millimeter per minute. The compressive strength that has been tested on the 4 samples and compared to the reference were conducted according to STM. The 2 leftover parts of each broken specimen in binding were cut and polished to obtain cubic specimens. The samples were tested in comparison by a Zwickroll 150 machine with 150 kN capacity. The loading rate was set to 1 millimeter per minute. As for reference measurement, it was like 63.4 compressive strength, and its flexural strength was 4.2, as we can see here in the green. For the gray, for mixture 2 was 23.8. As for flexural strength in green, we can see that it's 2.9 megapascal, reaching mixture 5 with 14.5 for compressive strength and 1.58 megapascal as flexural strength test. Thermal conductivity tests were performed using a C-therm TCI thermal analysis to obtain the thermal insulation behavior of rubberized samples. The lower is the thermal conductivity, the test in thermal, the best in thermal insulation. So regarding the reference, the thermal conductivity was 1.32, reaching mixture 5 with 0.81. What about density? It was for the reference 19.27. Mixture 5 arrived for 1468 meter cube. As for thermal conductivity reduction rate, we can see that reference was 0. It started to exchange between mixture 2 reaching mixture 5 between 41% reaching 39%. 4-point flexural tests were performed on Zwickroll's Z010 10 kilonewton universal testing machine beams were tested to evaluate the effect of the rubber aggregate on Young's modulus and flexural strength of the material. The span length was 180 millimeter and the loading rate was 1 millimeter per minute. For elastic modulus, as we can see here in the orange, is 5.56, as well as the elongation at break was 0.05 for the reference. As for compared for mixture 2 reaching mixture 5, it was 5.2 for elastic modulus, and the elongation was 0.03. As for mixture 5, it reached 1.82 with elastic modulus. Elongation at break, it reached 0.55%. Same microscopy methods were used to evaluate the tire rubber aggregate distribution in the cement matrix and the adhesion properties between rubber particles and cement paste. Then, imaging were performed using a mirror 3-phase scanning electron microscope in secondary electron mode. The concept behind the hollow inner design of the bricks is due to the characteristics of the shape, void percentage, and addition to the properties of the brick, using multi-physics analysis studied through console software. Void percentage and porosity of the 5 designed bricks is calculated, and it differs depending on the shape of hollow used, with a standard dimension of outer design block 350 by 250 millimeter. The softwares and machines used to develop the concept of the bricks and to study the characteristics and the properties of the shape and material used are COMSOL Multiphysics, Rhinoceros, and the 3D printing machine that is used to print the molds that are going to be used to pour the aggregate material in it. Characteristics behind the hollow brick inner shape. According to the design used as a square, it is a standard design. Number of hollow 11, length 45 millimeter with a porosity of 25%. Circular, which is also a standard design. Number of hollow 11, bridges 25 millimeter with a porosity 25%. Fractal, good for thermal insulation and potentially as acoustic insulation properties. Number of hollow is 10, length 10 millimeter, porosity 20%. Fractal is as an unconventional design for a brick, for a hollow brick. Hexagonal also is an unconventional design, good for mechanical properties. Number of hollow 11, length 27 millimeter with a porosity 24%. Hybrid is good matching between fractal and hexagonal properties as thermal insulation and mechanical strength. Number of hollow is 10, length for the hexagonal 27 millimeter plus length of fractal 10 millimeter, the porosity is 21%. This is here below we can see the topological optimization studies, the dimensions that are being used to be inserted in the COMSOL software in order to give good results. Here is the designed bricks that are going to be molded and tested. FEM-based mechanical analysis. 3D FEM-based mechanical analysis was performed using the structural mechanism modulus of COMSOL Multiphysics version 5.4. Static compression strength was simulated on the brick models considering the laboratory conditions in ASMEC standard test method for sampling and testing bricks and structural clay type. As we can see that the FEM mechanical analysis details were listed below as according to 14 megapascal. FEM-based mechanical analysis, here are the general properties of the mixture that are being used as a reference. You can check them according to the listed presentation. Here is the FEM-based mechanical analysis results and discussion. As we can see here, the UB brick is brick without hollow. We have the circular, the square, the hexagonal is the fractal, and also the hybrid. Cavity reduce the mechanical strength of the component, but improve its formability, properties, and post-crack performance. Among the perforated designs, the hexagonal structure exhibits the best mechanical behavior. HFB model ranks second in terms of strength properties of hollow bricks, which HFB is the hybrid brick. As for thermal analysis, FEM-based thermal analysis was performed using the heat transfer in solid model of COMSOL Multiphysics to evaluate the thermal insulation performance of brick prototypes. Thermal resistance was determined through steady state analysis as suggested by ISO 6946 standard. FEM-based thermal analysis, here we can see the analysis of the thermal according to an ambient condition and the law that has been used. FEM-based thermal analysis, we can see that air cavities in hollow bricks act as high thermal inertia size, improving thermal insulation properties than the unperforated model. High geometric complexity of the inner hash cavities maximize the thermal path of heat flow, resulting in greater thermal attenuation than the other architectures. Hybrid fractal design exhibits intermediate value between FB and conventional designs. This inner configuration combines the mechanical efficiency of hexagonal hollows with the thermal performance of fractal ones. Conclusion. Concerning material characterization, a cement paste containing rubber particles in the aggregate is much softer than cement paste without rubber. The crack would rapidly develop around the rubber particles during loading. As rubber has low stiffness compared to aggregate, presence of rubber particles in concrete reduces concrete mass stiffness and lowers its load-bearing capacity, but higher mechanical deformability. Factors affecting concrete density include aggregate density, air content, and the water and cement content in the design. A lower unit weight was obtained because of low specific gravity of rubber ships. Unit weight of mixture containing rubber decreased with increasing in the percentage of rubber content. It can classify as lightweight concrete, useful for thermal insulating applications. Depending on the selected material that has been tested, mixture 1 has been chosen for brick molding pouring due to its properties and performance. As related to the hollow shape of the brick design, it is suggested to work with the chosen hybrid hollow shape as its porosity is 21% and due to its mechanical properties, analysis, and performance, as well as its good in both compressive strength and thermal insulation. The future perspective, manufacturing with casting method and testing of the brick in order to validate the simulating data. Process brick molding pouring. After the material characterization, the mix with the best engineering performance will be selected based on the chosen compound. Brick with different internal architecture designed will be molded at Sapienza. Hexagonal shape, this is one of the examples of conceptual work that is going to be performed at Sapienza as a design for the structure of the brick. As example here, we can see that we have chosen, for example, hexagonal shape, and for the design that can support better mechanical properties and improvement in acoustic insulation. This is the dimension of the drawing in centimeter unit. Thank you.